Alright, so in this video we'll be looking at net ionic equations. Before we get right into it, let me just preface by mentioning that it's important that you need to know your solubility rules in order to do these types of problems. And I know different classes have different rules and protocols. I know some classes allow you to reference a list of solubility rules during an exam, whereas others require that you memorize them. So depending on whatever course it is that you are learning this material for, I recommend that you look into that, and so either have your solubility rules in mind or have a sheet ready to reference them in case you need them. Well, you will need them for these types of problems. Again, just have them with you if you want to follow along with the video. But anyway, kind of just starting off with a checklist or a common method that you can use to tackle these types of problems, right? Well, firstly, you always start by making sure that you're writing out the balanced molecular equation. And that's because if this is not right, in terms of your stoichiometry, or all the compounds aren't correct and, it's not a balanced equation, then the resulting net ionic that you're going to write from this is also obviously going to be incorrect. Secondly, you're going to want to split the aqueous species into their ions. This is the whole basis of the concept of the net ionic equation, right? You need to split only the aqueous soluble species into ions. This is, you're going to be, excluding anything that is not in the aqueous phase, that is liquids, gases, solids, really anything that is not in the species, that is not an aqueous species, will not be split into ions. They will just remain as they are. Okay, and number 3 will be to simply cancel out your spectator ions. And as you'll see, spectator ions are just the species that appear on both sides of the equation unchanged, or both sides of the expression unchanged, and so they will simply be canceled out. Okay, so let's just keep these 3 steps in mind as we look through the following problems. So let's start with a reaction between barium chloride and sodium sulfate. So barium chloride, that is BaCl2. Again, always keep in mind, or the states of your different compounds are in the equation. So barium chloride is aqueous, and it'll be reacting with sodium sulfate. That's Na2SO4, which is also an aqueous species. And this is actually a double replacement reaction. And so that means that your barium here is going to go with your sulfate, and your chloride is going to be reacting, or combining here with your sodium. And so that'll end up giving you barium sulfate, which is actually a solid. And we know this because, according to our solubility rules, all sulfates are going to be soluble, except for barium, lead, and calcium. And in this case, we do have barium associated with the sulfate, so that is going to precipitate out as a solid. And then we're going to have 2NaCl, which is aqueous. So this is going to be our balanced molecular equation here. And so that checks off step number 1, right? We make sure we have our balanced molecular equation. The next step will be to split our aqueous species into their respective ions. And so that means we'll be splitting up barium chloride, sodium sulfate, and NaCl, right? The barium sulfate, on the other hand, as being, it's a solid, it is not in the aqueous state, and so we will leave it as it is. So writing this out, we get barium plus 2Cl minus aqueous plus 2 Na plus aqueous plus sulfate aqueous, giving us barium sulfate in solid form and 2 Na plus. I'm just going to and 2Cl minus. All right, and then oh yeah, right. These are both aqueous as well. And so now that checks off step number 2. We split it up. I know it takes up a lot more room, so make sure you have enough room to write this out. But now we've split up our aqueous species into their ions, and we're now going to just do the last step, which is to cancel out our spectator ions. So looking through this mess of an expression, what do we see appearing on both sides of the reaction? Well, we see sodium ions are present, and our chloride ions are also present on both sides of the equation, whereas the barium and sulfate only appear on one side, and the barium sulfate also only appears on the product side. And so that leaves us with our net ionic equation to be barium ion plus sulfate ion gives us our precipitated solid barium sulfate, and this here is going to be your net ionic equation. And I forgot to mention earlier, this here given out in this full form of all the ions, this is going to be known as the total ionic equation, because it has all of the ions, including the spectator ions. And the expression or the equation that does not include the redundant species, those that appear on both sides, those spectator ions, is going to be your net ionic equation. All right, let's move on to the next one. Okay. So now let's look at an acid-base reaction, right? Last one was a precipitation reaction. Let's look at an acid-base reaction between hydrochloric acid and NaOH. Sodium hydroxide is going to be reacting with hydrochloric acid in this reaction. So we first start off by writing out the balanced molecular equation. That is, in this case, going to be HCl, which is aqueous, plus NaOH, also aqueous, which is going to give us NaCl and water. So this too can be seen as a double replacement, because we see the hydrogen is going to go to the hydroxide and the chloride is going to go with the sodium, which we see happening. Okay, and so now, again, this is going to be in the liquid phase. So we now have completed the first step, and moving on to the second step, we break the aqueous species up into their ions to give us a total ionic equation. So that's going to be H plus Cl minus plus Na plus OH minus is going to give us Na plus Cl minus. And here our water, our H2O, is in the liquid phase, which means that we do not break it up into ions. And so we get this to be our total ionic equation. So if you were asked to write out the total ionic equation, you would just leave your answer like this. But in our case, we're trying to find the net ionic equation, so we have to cancel out our spectator ions, which in this case are going to be chloride, as it appears on both sides, sodium, which also appears on both sides, leaving us with a net ionic of H plus OH minus is going to give us H2O. And so this is generally what you'll see when you are reacting a strong acid with a strong base. Firstly, you'll see that you're going to be getting a salt and water, and the net ionic is always going to be this. So if you do want to just keep that in mind, it is going to be useful. All right, now moving on to the next problem. Let's look at the reaction between zinc and hydrochloric acid again. Well, we'll be looking at solid zinc. Let me make this a bit more. Solid zinc reacting with our aqueous hydrochloric acid. Aqueous hydrochloric acid. And well, remember, this has to be a balanced equation. And so, well, one, you'll notice when you're reacting a solid with our HCl like this is going to be a single replacement reaction, meaning we know that our chloride from the HCl is going to go and combine with our zinc. And we also know zinc to have a charge of 2+, which means that we know, one, since we know that we will be forming zinc chloride, which requires 2 chloride ions, we know to put a 2 in front of our HCl to make sure that this stays balanced, and that means that we will also end up with an H2, which will be in the gaseous state, as hydrogen is a gas. So this here will be our balanced molecular equation for step 1. Now, for step 2, we break this up into its ions, giving us our total ionic equation. Okay, zinc is a solid, so it stays as it is. HCl can be broken up to 2H plus and 2Cl minus. ZnCl2. Zinc chloride is aqueous, and so it will be broken up. And hydrogen is a gas, so it stays as is. Now that is step 2. Finally, step 3, right, for our net ionic equation, we will have to cancel out the spectator ions, which in this case, if you'll observe, Cl minus appears on both sides. And so we get our net ionic to be Zn solid plus 2H plus aqueous gives us and here we go. This here will be our net ionic equation for this reaction. All right. And again, remember, if we did not correctly balance this single replacement reaction, we would have not gotten the right number of ions and thus not gotten the correct net ionic equation. So always remember and make sure that you are comfortable with balancing reactions. And let us look at one more example. So, in this one, let's look at the reaction between sodium nitrate and potassium chloride. So, sodium nitrate, that is aqueous, right? NaNO3 plus KCl, that's potassium chloride. And this is going to give us NaCl and potassium nitrate. Again, this is a double replacement. Okay, so now we break this up into its ions, right, to get the total ionic equation. So this is aqueous, so we do Na plus NO3 minus. I forgot to write aqueous here. Plus K plus CO minus, giving us Na plus and CO minus, K plus and NO3 minus our nitrate. So this here will be our total ionic equation. And what you'll see is now to get our net ionic, again, step 3 is to cancel out spectator ions. So what we see, sodium appears on both sides. We see nitrate does as well. So does potassium and chloride. So, well, really we have nothing remaining for our net ionic. So this is actually a kind of gotcha trick question that does come up on exams. It's a classic trick question, really. It's testing whether you know your solubility rules or not. So our net ionic equation, well, really is none. There is none, and that is actually a possible answer. That means that there is no reaction that takes place between these compounds. When we react sodium nitrate and potassium chloride, there is no reaction. And so again, if you remember, well, not if you remember, if you'll notice that if you did not know your solubility rules, we would not have been able to do this, because that we would have already been tripped up at the very first step, right? We know that all nitrates are always soluble. So we know that this potassium nitrate will dissociate into ions. If we did not know that, and were mistaken in thinking that this would actually precipitate out, we would get the wrong answer. So again, that just goes to show that you need to know your solubility rules in order to do these problems correctly. Alright, well, that brings us to the end of this video. So I hope that makes sense and you got some value out of this. If you did, please show your support by liking the video, subscribing, and leave in the comments what you guys would like to see next. And I'll see you guys in the next one.